So we've talked a little bit about kinetic and potential energy, and today we're going to talk about the conservation and conversion of this energy from one form to another. So you should know that energy cannot be created or destroyed. It can only change forms. And we've talked about laws of conservation before with mass and matter. We said matter cannot be created or destroyed, only transformed, and we said the same thing about mass. And now we're going to say the exact same thing about energy. So energy, you can kind of think about it, is all the sand in an hourglass. And although that sand can move from one end to another, that energy never escapes from that hourglass. So energy is always conserved. Even if it looks like we so-called lose energy, we are not losing energy. It is just changing forms. So energy always remains the same or in fixed quantities. So the sand can change positions from the top to the bottom and from the bottom to the top, but we still have the same amount of energy. So that's the same idea that we can change energy from kinetic to potential and back and forth. So energy can be converted from one form to another. You've seen this a lot in your life. One example is a burning candle. That chemical energy is being transferred to light and heat energy. When we burn fuel, it goes from chemical to heat to kinetic to electrical. Nuclear goes from nuclear to heat and light. And a spring goes from elastic potential energy to kinetic energy. So these energies are not being lost. They're just being transformed from one form to another. So when energy stored begins to move, the object transfers from potential to kinetic energy. So if you're standing still and you begin to run, your potential energy or your potential to do work changes from potential to moving energy or kinetic energy. And in this class, we're mostly concerned about kinetic energy to potential energy and back and forth. So like when an object is moving from one point to another, or when an object is undergoing some sort of change in height. Those are really the things that we're going to focus on in our conversions of energy. So when we talk about the difference and the transfer of kinetic energy to potential energy, one great example is a roller coaster. So if you're riding on a roller coaster, when you're at the very top of the hill before you start moving, you have a high amount of potential energy, specifically gravitational potential energy. And as your roller coaster begins to move, that gravitational potential energy changes from gravitational potential energy to kinetic energy. We're going to look a lot in this unit about this transfer from GPE to KE. So let's look at this ball that's in free fall. When the object is in its highest position here at the top, it is the highest amount of gravitational potential energy, and that should make sense to us because it is the highest height, and that is primarily what GPE is based on, in addition to mass. And as the object falls until it gets to the bottom, where its GPE is 0. At the top ball right here, our kinetic energy is 0 because our object is not moving. And as we go down, our kinetic energy increases. So there's an inverse relationship between this gravitational potential energy. As we get closer to the ground, our gravitational potential energy decreases. And as we get closer to the ground, our kinetic energy increases. So let's go ahead and look at this problem. A car is moving, it has a mass of 800 kilograms, its average speed is 5 meters per second. We want to find the energy of the moving car, and what form of energy is this? Well, it's a moving car, so it is, of course, kinetic energy. We're going to use our equation 1/2 mv squared in order to obtain the energy of the moving car. When we do that, we will get that our car's energy is 10,000 joules. Now, what energy does this car possess when it stops? Well, it possesses none because it is on the ground, which means it has 0 gravitational potential energy, and it's not moving, which means it has 0 kinetic energy. So what happens to the energy of this car when it stops? It's not being transferred from potential to kinetic or from kinetic to potential. Well, instead, it has been released as sound energy and heat energy. The heat energy mainly comes from the application of those brakes that allows you to stop. So the last thing I want to talk about real quickly in this video is how to do bar charts with potential and kinetic energy. We're going to lay out a couple rules for doing these. The first is that we are only going to fill 10 of these bars ever. That's the maximum amount of energy that we're going to have in all of these systems, which is 10 joules. So let's look at this first example. It says a pencil sitting on the edge of a table. Well, you should know that a pencil sitting on the edge of a table has absolutely no kinetic energy. It is sitting there, it's not moving. So I am going to say that this has 100% potential energy, and I would fill in that entire bar. When I talk about the number 2, it says a hot balloon floating in the air. It's not moving. So it also has 100% potential energy, and I'd fill in that entire bar as well. Now, let's look a little bit at a different example. It says a ball falling from a hot air balloon. Well, the ball's falling, so it's in motion, and we know that it's going to have both potential and kinetic energy. Now, it doesn't tell us where in the fall this ball is, so it's impossible for us to tell the relationship between potential and kinetic energy, but we know that the ball has both. So I can only fill in 10 bars total, so I'm going to fill in 3 for potential energy and 7 for kinetic. So that is how I would do my energy bar charts there. So I would like you to go ahead and complete 4, 5, and 6. There's also practice problems like these. We're also going to talk about them in class when I see you guys on Tuesday. So please practice these and bring these practice problems to class.